There is a question that sits beneath all other questions, not the question of how life arose, or how stars formed, or how galaxies assembled themselves into the great cosmic web we observe, stretching across billions of light years. Those are extraordinary questions, and they deserve the careful attention that science brings to them. But beneath all of them, prior to all of them, is the question that James Webb was ultimately built to address. What was there at the beginning? Not the beginning of Earth, or the beginning of the solar system, or even the beginning of the Milky Way. The beginning, the first moments of everything, the conditions from which all structure, all chemistry, all complexity, all life ultimately emerged. For most of human history, this question belonged to philosophy and theology rather than to science. The beginning was, by definition, beyond observation. Whatever happened in the universe's first moments was separated from us not merely by distance, but by time. By 13.5 billion years of cosmic history that had obscured, transformed, and overwritten the earliest conditions. And then James Webb launched, and it pointed its golden mirrors at the deepest, oldest, most distant objects it could find. And it read in the ancient light of the universe's first billion years, a story that our best models had not fully anticipated, a story of galaxies that were too massive, too bright, too chemically complex for where they appeared in cosmic time, a story of structures that formed faster than the physics was supposed to allow, a story of a universe in its infancy that was, by every measure, stranger and more violent and more productive than the theoretical framework that had guided astronomy for decades had predicted. That story is not finished. The data is still being analyzed. The papers are still being written. The debates are still ongoing among researchers who have spent their careers building the models that Webb's observations are now testing, and, in some cases, challenging. But what has already been found is remarkable enough to explore tonight. Slowly, carefully, with wonder as our compass and honesty about uncertainty as our guide, we have the whole night. The universe has been waiting 13.5 billion years to be seen this clearly. It can be patient a little longer. As we begin our journey tonight, let us understand why the James Webb Space Telescope is able to see the early universe in ways that no previous instrument could. Because the answer is not simply that Webb is larger or more powerful, though it is both. The key lies in the nature of the light itself. When a galaxy is very far away, when it exists at a great distance from us in an expanding universe, the light it emits is shifted to longer wavelengths by the time it reaches us. This is the cosmological redshift we have explored in other journeys. The universe expands, space stretches, and the wavelength of light traveling through that expanding space stretches with it. For the most distant galaxies, those that existed when the universe was less than 1 billion years old, at what astronomers call high redshift, the light that originally left those galaxies as ultraviolet and visible radiation has been stretched by the expansion of the universe over 13+ billion years into the infrared portion of the electromagnetic spectrum. The light is invisible to human eyes. It is invisible to Hubble, which was designed primarily for visible and ultraviolet observation. It is, however, precisely the range of wavelengths that Webb was designed to detect. Webb's primary mirror, that iconic arrangement of 18 gold-coated hexagonal beryllium segments spanning 6.5 meters from edge to edge, is optimized for infrared light. The gold coating, chosen for its excellent reflectivity at infrared wavelengths, catches photons that would pass undetected past a conventionally coated mirror. The telescope's instruments, NIRCam, NIRSpec, MIRI, and the fine guidance sensor are calibrated for wavelengths from near-infrared to mid-infrared, covering the spectral range where the light of the early universe arrives. To detect infrared light from distant objects, the telescope itself must be extraordinarily cold. Heat generates infrared radiation, and if Webb's instruments were at room temperature, their own thermal emission would overwhelm the faint signals they are trying to detect. Webb's sunshield, that 5-layered, tennis court-sized membrane, blocks the heat of the sun and keeps the telescope's cold side at approximately -230 degrees Celsius. Some instruments are cooled further still. This combination, large collecting area, infrared sensitivity, extreme thermal stability, gives Webb the ability to detect the light of galaxies that existed when the universe was a few percent of its current age. Galaxies that no previous telescope could observe with this level of detail and spectral resolution. And what Webb finds in that ancient light has been, repeatedly, surprising. Let us follow the moment when Webb's capabilities were first dramatically demonstrated. The release of the first Webb Deep Field image in July 2022, and understand what it revealed. The concept of the deep field comes from Hubble. In 1995, Hubble was pointed at an apparently empty patch of sky and observed it for 10 consecutive days. The resulting Hubble Deep Field image revealed thousands of galaxies in a patch of sky that appeared empty to the naked eye, transforming our understanding of the universe's large-scale structure and galaxy populations. Subsequent deep field observations by Hubble extended and deepened this picture. Webb's first deep field image, released by NASA on July 11, 2022, showed the galaxy cluster SMACS 0723, approximately 4.5 billion light-years from Earth. The cluster itself is impressive, a massive concentration of hundreds of galaxies whose combined gravitational fields acts as a natural lens, magnifying and distorting the light of galaxies behind it through gravitational lensing. But the background galaxies, the faint, arc-shaped, distorted images visible throughout the field, are what captivated astronomers. These are galaxies far behind the cluster, their light bent and amplified by the cluster's gravitational field, appearing to us as stretched arcs and rings. Some of these background galaxies are among the most distant objects ever observed, their light representing the universe as it appeared billions of years ago. The image was, by any standard, extraordinary. It showed more galaxies in a patch of sky the size of a grain of sand held at arm's length than Hubble could see in the same field in weeks of observation. The sensitivity and resolution of Webb's instruments produced a view of the deep universe with a clarity that left astronomers visibly moved when the image was first revealed. But the image was only the beginning. It demonstrated what Webb was capable of. The science, the spectroscopy, the measurements of redshift and composition and mass, the systematic survey of the early universe would follow. And when it did, the surprises began. As we continue, let us explore the finding that generated the most scientific discussion and the most public excitement from Webb's early observations: the detection of galaxies that appeared too massive for their age. The standard model of galaxy formation, called lambda CDM cosmology, for cold dark matter with a cosmological constant, made specific predictions about what the early universe should look like. These predictions were built from first principles: the known laws of gravity, the observed distribution of dark matter halos inferred from simulations, the measured properties of the cosmic microwave background, and decades of observations of galaxies at lower redshift. The predictions were reasonable and well tested. Galaxies grow by accreting gas and by merging with other galaxies. Both processes take time. In the early universe, there has been less time for these processes to operate. The expectation was that galaxies at redshift 10 and above, corresponding to the universe being less than 500 million years old, would be small, faint, irregular, proto-galactic fragments in the early stages of assembly. Webb observed galaxies at these redshifts and found some that were, according to the observed brightness and the spectral properties of their light, significantly more massive than the models predicted. One paper, published in 2022 and subsequently much discussed, identified a population of galaxy candidates at very high redshift whose inferred stellar masses were comparable to massive galaxies in the much later universe. The implication, if the mass estimates were correct, was that these galaxies had assembled an extraordinary amount of stellar mass in a very short period of time. Astronomers were genuinely surprised. Some described the finding as potentially challenging to the Standard Model. The popular press, with characteristic enthusiasm, declared that Webb had broken cosmology. It had not broken cosmology, but it had identified something that needed explanation. And the process of constructing that explanation has deepened our understanding of the early universe in ways that are themselves fascinating. Let us follow the scientific community's careful work to understand the unexpectedly massive early galaxies. Because the range of explanations being explored illuminates the complexity of the early universe. The first consideration is observational uncertainty. Estimating the stellar mass of a distant galaxy is not a simple measurement. It involves modeling the observed infrared fluxes in multiple filter bands with spectral energy distribution models that make assumptions about the age distribution of the stars, the initial mass function, the distribution of stellar masses when a population of stars forms, the amount of dust obscuration, and the contribution of emission lines from ionized gas to the photometric measurements. Each of these modeling assumptions carries uncertainty. For the most extreme high redshift candidates, some researchers found that careful reanalysis with different modeling assumptions produced lower mass estimates, more compatible with the standard predictions. Some of the most extreme early candidates turned out, upon spectroscopic follow-up, to be at lower redshifts than their photometric colors had suggested. But not all of the tension was explained away by measurement uncertainty. A population of high redshift galaxies remains that is genuinely more massive than standard models predicted. The second category of explanation involves the efficiency of star formation in the early universe. Standard models assume that only a modest fraction, typically a few percent, of the gas in a dark matter halo is converted into stars at any given time. Much of the gas is expelled by stellar feedback. The radiation, winds, and supernova explosions of massive stars that heat and drive gas out of the galaxy. If early galaxies formed stars more efficiently, converting a larger fraction of their gas into stars before stellar feedback could expel it, they could build up stellar mass faster. Some theoretical arguments suggest that the conditions of the early universe, higher gas densities, different thermal physics, different feedback mechanisms, could naturally lead to higher star formation efficiency. The third explanation involves the possibility that some of the luminosity attributed to stellar mass actually comes from active galactic nuclei, supermassive black holes at the centers of these early galaxies accreting material and producing prodigious amounts of radiation. A bright active nucleus could make a galaxy appear more massive in photometric observations than its stellar population alone would warrant. The current consensus is that the tension is real but not catastrophic, that the Standard Model requires refinement in its treatment of early star formation efficiency and stellar feedback, but does not require fundamental revision of its foundational physics. As we continue our exploration, let us turn to one of the most scientifically productive areas of Webb's early universe observations: the study of the epoch of reionization, the period when the first luminous objects transformed the state of the intergalactic medium. We have explored the epoch of reionization in other journeys, the period from approximately 200 million to 1 billion years after the Big Bang, during which the radiation from the first stars and galaxies was converted the neutral hydrogen of the cosmic dark ages back into ionized plasma. Webb has been providing for the first time a detailed observational window into this epoch through several complementary approaches. The first is direct observation of galaxies during the reionization epoch. Galaxies at redshifts above 6, corresponding to the universe being less than 1 billion years old. Webb's Inner spectrograph can measure the spectra of these galaxies with enough detail to detect specific emission lines, particularly the Lyman alpha emission line of hydrogen, which is produced when ionized hydrogen recombines. The detectability of Lyman alpha emission is sensitive to the amount of neutral hydrogen between the galaxy and us. Neutral hydrogen absorbs Lyman alpha photons very efficiently, so if the intergalactic medium is partially neutral, Lyman alpha emission from distant galaxies is suppressed. By measuring how Lyman alpha emission changes with redshift, how its detectability varies across the reionization epoch, Webb is mapping the progression of reionization. Where and when did reionization begin? Did it proceed uniformly, or did some regions of the universe reionize before others? The answer emerging from Webb's data is that reionization was patchy, that some regions of the universe became transparent to ionizing radiation earlier than others, driven by local concentrations of luminous galaxies that created expanding bubbles of ionized gas before those bubbles grew and merged to complete the global reionization. This patchy character of reionization is not surprising. It was theoretically expected, but Webb is now providing the observational evidence that confirms it and allows the details of its spatial structure and temporal progression to be characterized. Let us explore one of the specific questions that Webb is addressing about the epoch of reionization. The question of what sources were responsible for driving it. Reionization requires a sustained supply of ionizing photons, ultraviolet photons energetic enough to ionize hydrogen. The question of what provided those photons has been actively debated. The candidates are primarily galaxies, specifically the young, massive, hot stars within early galaxies that produce copious ultraviolet radiation, and potentially quasars, the actively accreting supermassive black holes that are among the most luminous objects in the universe. The challenge with galaxies as the drivers of reionization is the escape fraction. Not all of the ionizing photons produced by stars within a galaxy escape into the intergalactic medium. Most are absorbed by gas and dust within the galaxy itself, never reaching the surrounding neutral hydrogen. Only the fraction that escapes, the escape fraction, contributes to reionization. In nearby galaxies, the escape fraction is typically very low, a few percent or less, but theoretical arguments suggest that early galaxies which were smaller and had different gas distributions and stellar populations might have had higher escape fractions. Webb's spectroscopic observations of early galaxies are providing constraints on their properties. Their star formation rates, their stellar populations, their ionizing photon production rates that allow the ionizing photon budget to be estimated. The question is whether the observed galaxy population can produce enough escaping ionizing photons to complete reionization on the observed timeline. The emerging picture is that galaxies here, particularly the numerous faint galaxies that are individually too faint to observe, but whose collective contribution is significant, were likely the dominant drivers of reionization, with quasars playing a secondary role at later times when their abundance increased. This has implications for how we think about the sources of reionization and the role of different types of objects in the early universe's transformation from neutral to ionized. As we continue, Let us explore what Webb's spectroscopic observations of early galaxies are revealing about the chemical evolution of the universe. Because the chemical story of the early universe is both scientifically profound and deeply connected to the question of what made our own existence possible. The Big Bang produced hydrogen, helium, and trace lithium. Every other element in the universe, every atom heavier than lithium, was made later, in stellar interiors and in stellar explosions. The process of enriching the universe with these heavier elements, from the pristine hydrogen-helium gas of the early universe to the chemically rich environment of the modern universe, where rocky planets and complex biochemistry are possible, took time and required the births and deaths of successive generations of stars. Webb's spectroscopic capabilities allow the chemical abundances of distant galaxies to be measured. The spectra of these galaxies contain emission lines from ionized atoms, oxygen, nitrogen, carbon, sulfur, whose strengths relative to each other encode the ratios of different elements in the galaxy's gas. These ratios reflect the history of star formation and stellar death in that galaxy. How many generations of stars have lived and died, seeding the surrounding gas with their nucleosynthetic products. In the most distant galaxies, Webb has been able to spectroscopically characterize those at redshifts above 7, corresponding to the universe being less than 700 million years old. The chemical abundances are low compared to the modern universe. These are chemically primitive galaxies with element ratios that indicate only one or a few generations of stellar enrichment. But they are not chemically primitive in the extreme way that was expected. Some high redshift galaxies show chemical enrichment levels that suggest more stellar processing than simple models of the first generation of stars would predict. Some show unexpected ratios of specific elements that indicate unusual stellar populations or unusual star formation histories. The chemistry is telling a story of rapid, efficient stellar cycling, of gas being converted to stars, the stars dying and enriching the gas, and the enriched gas forming new stars, all on timescales of tens to hundreds of millions of years in the very early universe. The universe learned chemistry faster than we expected. Let us explore a specific chemical anomaly that Webb has found in some early galaxies, one that has generated considerable scientific discussion because it points towards stellar processes that were not fully anticipated. In several high redshift galaxies observed spectroscopically by Webb, the ratio of nitrogen to oxygen is unexpectedly high. In the chemical enrichment of galaxies as we understand it from nearby objects, nitrogen is primarily produced by intermediate mass stars that process it through the CNO cycle and return it to the interstellar medium during their late evolutionary stages as asymptotic giant branch stars, or in stellar winds. Oxygen is primarily produced by massive stars and dispersed in core collapse supernovae. The timescales for these two processes differ. Oxygen enrichment proceeds on the timescales of massive stellar evolution, millions of years. Nitrogen enrichment from intermediate mass stars proceeds on longer timescales, hundreds of millions of years, as those stars age and reach their nitrogen-producing evolutionary stages. Finding high nitrogen to oxygen ratios in galaxies that existed when the universe was less than 1 billion years old, before the timescales for normal nitrogen enrichment have elapsed, is unexpected. It suggests either that the massive stellar populations of early galaxies were chemically unusual in ways that enhanced nitrogen production, or that some other enrichment process was operating. One proposed explanation involves Wolf-Rayet stars, the stripped cores of massive stars that produce nitrogen-rich winds, whose contribution to chemical enrichment might have been more significant in the early universe's stellar populations. Another involves the possibility of supersolar nitrogen production in very massive stars under conditions specific to the early universe's environment. Whatever the explanation, the unexpected capsule signatures in early galaxies are telling us that the stellar populations of the early universe were not simply scaled versions of modern stellar populations. They were different in composition, in mass distribution, in evolutionary behavior. The early universe did not simply run the same processes as the modern universe, only faster. It ran different processes. As we continue our journey through what Webb has revealed about the universe's beginning, let us address one of the most profound puzzles it has uncovered: the presence of extremely massive black holes at very early cosmic times. Active galactic nuclei, the brilliantly luminous centers of galaxies powered by material accreting onto supermassive black holes, have been observed at redshifts above 7, corresponding to the universe being less than 700 million years old. Some of these objects have estimated black hole masses in the hundreds of millions to billions of solar masses. The puzzle is fundamental and comes down to time. Growing a supermassive black hole through standard accretion processes requires time. The Eddington limit, the maximum luminosity a black hole can sustain without its own radiation blowing away the infalling gas, sets a maximum accretion rate. Growing a black hole from the mass of a stellar remnant, a few solar masses, to a billion solar masses at the Eddington limit without interruption takes approximately 700 million years. 700 million years is roughly the age of the universe when the most massive early quasars are observed. This means there is essentially no margin. The black holes would have had to begin accreting essentially from the moment they formed, at the maximum possible rate without interruption to reach their observed masses. This seems physically implausible. Accretion is not constant or uninterrupted. Galaxies merge and disrupt their gas supplies. Quasar feedback, the radiation and winds from the accreting black hole, heats and expels gas, reducing the accretion rate. The conditions for sustained Eddington rate accretion over hundreds of millions of years are extraordinary. Webb is addressing this problem through systematic surveys of early active galactic nuclei, measuring their masses, their accretion rates, and their relationship to their host galaxies. The data is providing constraints on the formation and growth mechanisms. Let us explore the theoretical mechanisms that have been proposed to explain the existence of billion solar mass black holes in the early universe, because this is one of the most active areas of theoretical astrophysics, and Webb's observations are helping to discriminate between them. The first mechanism is the most conservative, massive stellar remnants. When the first population 3 stars, those extraordinarily massive objects formed from metal-free gas, ended their lives, the most massive among them may have left behind black hole remnants of hundreds to perhaps 1,000 solar masses. These massive seed black holes could then grow through accretion, reaching supermassive scales if conditions were favorable. The challenge with this pathway is that even starting from 1,000 solar masses and accreting at the Eddington rate, reaching a billion solar masses in 700 million years is barely possible. Any periods of sub-Eddington accretion, any breaks in the growth rate, make it impossible. The second mechanism is direct collapse. Under specific conditions in the early universe, primarily the presence of a radiation field that prevents molecular hydrogen from forming and cooling the gas efficiently, a massive gas cloud might collapse directly into a massive black hole without going through a stellar phase. The result would be a seed black hole of perhaps 10,000 to 100,000 solar masses. Starting from this larger seed significantly relaxes the time constraint. The third mechanism is super-Eddington accretion. Under certain physical conditions, particularly in the presence of very high gas densities and specific accretion geometries. Black holes can accrete at rates exceeding the Eddington limit. The radiation produced is partially trapped by the infalling gas, rather than being free to blow it away. Super Eddington and Tungsten accretions is theoretically possible and may be occurring in some observed systems. Webb's contribution is observational. By finding and characterizing active galactic nuclei at very high redshift, measuring their luminosities, estimating their black hole masses, and relating them to their host galaxy properties, Webb is building a statistical sample that can test these theoretical mechanisms. The growing census of early active galactic nuclei from Webb suggests that massive black holes were surprisingly common in the early universe, more common than the most conservative models predicted. The formation and growth of these objects is now recognized as a fundamental aspect of early cosmic evolution, intertwined with the formation of the galaxies that host them. As we continue tonight, let us explore what Webb is revealing about the large-scale distribution of matter in the early universe. Because the story of the beginning is not just a story of individual galaxies, but of the cosmic web in which they are embedded. The cosmic web, the large-scale structure of filaments, sheets, nodes, and voids that organizes matter on scales of tens to hundreds of millions of light years, is one of the most striking features of the modern universe. But this structure had to form from the nearly uniform early universe. Understanding when and how the cosmic web assembled itself is one of the fundamental questions of observational cosmology. Webb is providing the first detailed maps of galaxy distributions in the high redshift universe, identifying overdense regions where multiple galaxies cluster together, tracing the earliest filaments and protoclusters. A protocluster is an overdense region of the early universe that will, over billions of years, collapse under gravity into a massive galaxy cluster, one of the largest gravitationally bound structures in the universe. Finding protoclusters in the early universe, observing the seeds of the largest structures before they have fully formed, tests models of structure formation and tells us about how the early cosmic web was assembled. Webb has identified several candidate overdensities in the high redshift universe, regions where multiple galaxies at the same redshift are found in proximity, suggesting they are physically associated and will eventually merge into a cluster. Some of these overdensities appear to exist when the universe was less than 1 billion years old. Finding significant clustering at these early times tells us that the density fluctuations that seeded structure form, those tiny variations in the cosmic microwave background, were sufficient to produce significant overdensities within the first billion years. The cosmic web was not slowly, gradually assembling over the entire age of the universe. Its seeds were present very early, and its early stages were already visible when the universe was less than 10% of its current age. Let us explore what Webb's images reveal about the shapes and structures of the earliest galaxies, because the morphology of a galaxy is a record of its formation history. And the shapes of early galaxies tell us something profound about the processes that built them. In the nearby universe, galaxies come in a variety of well-defined morphological types. Spiral galaxies, like the Milky Way, have disk-like structures with organized spiral arms, reflecting their formation from rotating gas disks and their relatively quiescent recent histories. Elliptical galaxies, smooth, featureless, roughly spherical, or ellipsoidal, are thought to be the remnants of galaxy mergers, their original disk structures scrambled by the violent gravitational interactions of collisions. In the high redshift universe, the morphological picture is dramatically different. Webb's high-resolution infrared imaging of early galaxies reveals objects that are predominantly irregular, clumpy, and compact. lacking the organized spiral structure of modern disk galaxies, but also lacking the smooth, featureless structure of ellipticals. The clumpy character of early galaxies is particularly informative. The clumps, dense, bright regions within the irregular body of the galaxy, are thought to be regions of intense star formation. In the early universe, the conditions within galaxies were different from today. Gas fractions were higher. A larger fraction of the galaxy's baryonic mass was in the form of cold gas rather than stars. The instabilities that can develop in a gas-rich rotating disk, the same type of instability responsible for the spiral structure of modern galaxies, operated more vigorously in these gas-rich systems, producing dense concentrations of gas that fragmented and formed stars in intense, localized bursts. The compact sizes of early galaxies are striking. Many high redshift galaxies are significantly smaller in physical size than galaxies of similar stellar mass in the modern universe. A galaxy that will eventually be as large as the Milky Way exists at early times in a far more compact configuration. Its stars packed into a smaller volume. Its star formation concentrated rather than spread across a large disk. These compact configurations are thought to gradually grow through mergers and through the accretion of surrounding gas and smaller satellite galaxies into the larger, more extended structures we see in the nearby universe. As we approach the final chapters of our exploration tonight, let us sit with an honest assessment of where standard cosmological models stood before Webb and where they stand now. Because this is where the historical significance of Webb's discoveries is most clearly framed. Lambda CDM cosmology, the standard model of cosmology, is one of the most successful scientific theories ever developed. It accounts for the large-scale structure of the universe, the detailed pattern of temperature fluctuations in the cosmic microwave background, the abundance of light elements produced by Big Bang nucleosynthesis, the expansion history of the universe traced by supernova observations, and many other observational facts with extraordinary precision. The foundational physics of lambda CDM is not in question. The Big Bang happened. Dark matter exists in the form of cold, weakly interacting particles that provide the gravitational scaffolding for structure formation. Dark energy exists in the form of a cosmological constant or similar component that drives the accelerating expansion of the universe. These conclusions are supported by such a diversity and volume of evidence that they represent as solid a scientific consensus as exists anywhere in physics. What Webb's observations are testing, and in some cases challenging, is not the foundational physics, but the astrophysical processes that operate within that framework. Galaxy formation, star formation, feedback processes, black hole growth. These are complex, multi-scale, multi-physics phenomena that cannot be derived from first principles alone. They must be modeled with simplifying assumptions, empirical calibrations, and computational approximations. The surprises from Webb, the unexpectedly massive early galaxies, the unexpected chemical abundances, the unexpected abundance of early massive black holes, are telling us that these astrophysical models need refinement. Not that the fundamental cosmological framework is wrong, but that the specific processes of early galaxy formation were more efficient, more violent, and more complex than the models had fully captured. This is how science progresses, not through the overthrow of well-established frameworks, but through the refinement of the processes within those frameworks, driven by new observations that reveal what the models missed. Let us address a separate but related puzzle that Webb has been contributing to. The Hubble tension, because it represents a potential crack in the standard cosmological framework that goes deeper than the astrophysical modeling issues we have been discussing. The Hubble constant is the rate at which the universe is expanding, the proportionality between the recession velocity of a distant galaxy and its distance from us. It is one of the most fundamental parameters in cosmology. Its value determines the age and size of the observable universe and enters into essentially every cosmological calculation. The problem is that two independent methods of measuring the Hubble constant give different answers. The first method uses the cosmic microwave background, the precise pattern of temperature fluctuations in the oldest light in the universe. The Planck satellite's measurements of the CMB, combined with the standard cosmological model, give a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method uses the cosmic distance ladder, a chain of distance measurements using standard candles, particularly Cepheid variable stars and type Ia supernovae. These measurements, refined over decades by the Hubble Space Telescope and now extended by Webb, give a Hubble constant of approximately 73 kilometers per second per megaparsec. The discrepancy is approximately 8 to 10%. In a field where measurements are made to precisions of a few percent, an 8 to 10% discrepancy between two independent methods is significant. It is called the Hubble tension, and it has been growing more significant as each method has been refined, becoming not less but more pronounced as the statistical uncertainties in each measurement have been reduced. Webb has contributed to this problem by providing independent measurements of Cepheid distances at greater precision and to greater distances than Hubble could achieve. Webb's Cepheid measurements have confirmed and in some cases strengthened the high-value measurements of the Hubble constant from the distance ladder, making it harder to attribute the tension to systematic errors in the distance ladder. If the tension is real, if the universe is genuinely expanding faster than the standard cosmological model predicts, it would indicate new physics beyond the standard model, new components of the universe, new processes in the early cosmos, a modification to the physics of dark energy or dark matter. This would not merely refine the standard model, it would fundamentally extend it. As we near the conclusion of our journey tonight, let us sit with the phrase in our title that Webb's discoveries will rewrite history and examine what that actually means. Rewriting history is a phrase that gets applied liberally and often imprecisely. Most scientific discoveries do not rewrite history. They extend knowledge, adding new chapters to an existing story rather than revising the chapters that came before. But there are genuinely transformative discoveries, observations or theoretical breakthroughs that do not merely extend what is known, but change the framework within which everything is understood. The heliocentric model, the theory of evolution, general relativity, the Big Bang, the discovery of dark energy. These discoveries did not merely add to our knowledge. They reorganized it. They changed what the existing knowledge meant. Webb's discoveries exist on a spectrum of significance. Some, the characterization of exoplanet atmospheres, the detailed mapping of nearby star-forming regions, the beautiful images of galaxies and nebulae, extend and enrich our knowledge within the existing framework. They are scientifically important and wonderfully revealing without requiring us to revise our fundamental understanding. Others, the unexpectedly massive early galaxies, the unexpected chemical abundances, the Hubble tension contributions, are pointing at something more significant. Not necessarily a revolution in the foundational physics, but a genuine revision in our understanding of how the early universe worked, of what processes operated, at what efficiencies, in what sequences. The rewriting that Webb is enabling is the rewriting of the early chapters of the universe's story, the chapters that describe not the Big Bang itself. We did not see that, and Webb does not change our understanding of it significantly, but the first billion years. The formation of the first stars, the first galaxies, the first black holes, the first heavy elements. The conditions of the universe when it was young. These are the chapters that, before Webb, were the most poorly observed. The chapters written most heavily in theory rather than in data. And they are the chapters that Webb is now filling in with observations. Specific, quantitative, surprising, illuminating observations. The history being rewritten is not human history. It is cosmic history. The history of the universe itself. From its beginning, let us be honest. Near the end of our exploration about what Webb has not yet answered, and what may be beyond its capacity to answer, because the depth of remaining mystery is itself a part of the story. Webb cannot see the very first stars. Population 3 stars, those extraordinary massive objects formed from metal-free gas in the first 200 million years of the universe, have not been directly detected by Webb. They are too distant and too early for even Webb's sensitivity to pick out individual objects. What Webb can do is search for their chemical signatures, the specific abundance patterns they would leave in the gas of subsequent generations of stars and galaxies, and observe the galaxies they belong to in statistical aggregate. But the first stars themselves remain, for now, theorized rather than observed. Webb cannot directly observe the cosmic dark ages, the period before the first stars, when the universe was filled with neutral hydrogen and no sources of light existed. The universe at that time is essentially opaque to all forms of electromagnetic radiation that Webb or any optical or infrared telescope can detect. The Hubble tension may or may not be resolved by Webb. Existing measurements have strengthened rather than resolved the tension. Whether the solution lies in systematic errors not yet identified in the distance ladder measurements or in new physics beyond the standard model is genuinely uncertain. The nature of dark matter remains unknown. Webb does not directly detect dark matter. It maps its effects through gravitational lensing and the distribution of luminous matter within halos. The particle physics identity of dark matter is not a question Webb can answer. The nature of dark energy, that constituent of the universe that makes up 68% of its total energy content and drives the accelerating expansion, is similarly beyond Webb's capacity to address directly. The deepest questions about the origin of the universe, what happened before the Big Bang, whether inflation occurred and in what form, whether the universe is one of many, are not questions that observations with any telescope, however powerful, can currently address. The map of the unknown is vast. Webb has filled in some blank spaces. It has revealed that other blank spaces were more interesting than they appeared, and it has opened new questions that did not exist before it flew. That is what the best science always does. And so we arrive, gently and without hurry, at the end of our journey tonight. We have traveled far together, from Webb's sunshield and golden mirrors floating in perfect thermal stability at the second Lagrange point, to the deep field images that revealed thousands of galaxies in a patch of sky that appeared empty, to the specific surprising findings that those observations contain. We have followed the unexpectedly massive early galaxies, those objects too bright, too chemically developed, too structurally substantial for where they appear in cosmic time. And we have explored the range of explanations that astronomers are constructing to account for them. Measurement uncertainty that has been partially, but not entirely resolved. Star formation efficiency higher than standard models assumed. Active galactic nuclei contributing to the observed luminosity. All of these combined in proportions that the ongoing analysis is working to determine. We have traced the epoch of reionization as Webb is mapping it, the patchy source-driven transformation of the intergalactic medium from neutral to ionized, driven primarily by the collective ultraviolet output of early galaxies, rather than by a few dominant sources. We have followed the chemical evolution of the early universe as Webb spectroscopy is revealing it. The rapid, efficient enrichment of early galaxies, with heavy elements produced by successive generations of massive stars, the unexpected nitrogen to oxygen ratios that point toward unusual stellar populations in the early universe. We have sat with the supermassive black hole problem, those billion solar mass objects that existed when the universe was barely 700 million years old, challenging our understanding of how black holes grow, requiring formation mechanisms that the standard picture of stellar remnant seeds growing through Eddington-limited accretion cannot easily accommodate. And we have been honest about the Hubble tension, that persistent, deep discrepancy between two independent measurements of the universe's expansion rate that Webb has contributed to rather than resolved, and that may, if it survives further scrutiny, require new physics beyond the standard cosmological model. All of this, taken together, held carefully, considered with the full weight of what it means, represents something genuinely significant in the history of human knowledge. For most of human history, the beginning of the universe was inaccessible to observation. The first billion years, the period when the structures that define the universe we inhabit were being assembled from the primordial hydrogen gas of the post-recombination universe, were known only through theory, through models that were carefully constructed and internally consistent and well motivated by physical principles, but that were not yet constrained by the detailed observations they required. Webb has changed that. For the first time, we have specific, spectroscopic, high-resolution observations of the universe as it existed in its first billion years. Not the statistical averages of populations too faint to resolve individually. Not the theoretical inferences from the present state of the universe worked backward through models, but actual galaxies, actual spectra, actual measurements of actual objects that existed when the universe was a few % of its current age. And what those actual observations show is a universe that was, in its early chapters, more extreme than we expected, more efficient in its star formation, more chemically evolved more quickly, more abundant in massive black holes, more actively violent in its merger dynamics, more productive in every sense of that word than the models, for all their sophistication, had fully captured. This is not a failure of science. It is science working precisely as it should. The models were the best that could be constructed from the available data. The new data from Webb is revealing where they were incomplete. The response of the scientific community to examine the observations carefully, to consider alternative explanations, to refine the models to accommodate the new findings, is the normal, healthy, productive operation of science at the frontier. And the frontier has moved. The first billion years of cosmic history, once the most theoretically described and least observationally constrained period in cosmology, is now an active field of empirical investigation. Webb is returning data continuously. Papers are being written. Models are being revised. The picture is becoming more detailed, more grounded, more constrained. Tonight, as you rest, somewhere above the atmosphere, above the weather, above the clouds, above the thin blue line of sky that from below looks infinite but from above looks gossamer and fragile. A telescope is turning its golden face toward the ancient light of the early universe, collecting photons that have been traveling for over 13 billion years, spreading them into spectra, reading the chemical fingerprints of galaxies that existed before our sun was born. It is finding things that surprise us. And in those surprises, in the specific ways that the universe's beginning differs from what we expected. The history of everything is being rewritten, not erased and replaced, but enriched, deepened, made more specific, made less theoretical and more real. The universe has had a beginning. It was strange and violent and extraordinarily productive. And we are, for the first time, beginning to see it as it actually was, not as a theoretical reconstruction, but as a direct observation. That is one of the most extraordinary achievements in the history of science. And it is happening now. Rest in that knowledge tonight, in the awareness that we live at a remarkable moment when the instruments exist, the technology works, and the ancient light is arriving at a detector precise enough to read it. The beginning of everything is being seen for the first time, and what it shows us is more beautiful, more complex, and more surprising than we knew to expect. Thank you for exploring with us tonight. May your rest be as deep as the time between the Big Bang and the first light, and as full of quiet possibility as the darkness before the first stars ignited.